Lesson 112. Today, what we're going to go through is transformations. What a transformation is when we somehow transform our graph so that one graph no longer looks like the other graph. Just to give you a quick teaser here, what it'll make visually happen is you may have one graph, let's just say it's a parabola. I'm going to draw a parabola going through the origin here. You might have one graph that resembles a parabola. And what we'll do is we'll end up coming behind it and saying, okay, well, we could transform this graph. And when we transform it, maybe we just shift it over like I've done here. Maybe I have a graph that's been transformed by translating the graph. That's what you would call this here, a translation. Translating it is if you just shift it over. So sometimes you'll see me just shift it over. Other times we might flip it upside down. That's called a reflection. So you'll see sometimes where we flip the graph, maybe translate the graph as well. So that would be called a reflection. And one other transformation you might see is I might stretch it or shrink it. The word we're going to use is dilate. So I might dilate the graph where I stretch it or shrink it to make it larger or smaller, something like that. So you notice the graph would now be a different shape and size. So three things that might happen. We might shift it, we might reflect it, we might dilate it. Those are the three things you're going to see today, okay? So that's what we're doing when we construct a function that's an additive or multiplicative transformation of another function. That's what I mean. We're either going to reflect, translate, or starts with a D, dilate. That's it. Okay, so first, I'm going to start with what's called a parent function. A parent function is the most simple function of a family of functions. So what I was just doing on the previous page is I was showing you parabolas. The original parabola would be the parent function, the one that goes through the origin. So the most basic function is called the parent function. Most simple, you could say most basic if you like. Some types of family functions we're going to see today: linear, quadratic, cubic, square root. We'll also see absolute value that I can remember. That might be it for today. They will each share certain similarities, and they'll also have some differences. All right. So as I begin this here, I have some parent functions down. On this slide, these are showing you the different types of polynomial parent functions. There are 4 different ones. These are polynomial parent functions. Now, why is that? This is a polynomial, if you remember, is where you have x to some power, and that power has to be a whole number and it has to be a positive number. So here, if it's a constant flat graph, this is actually kind of like it's x to the 0 power. So that would be a constant line. That would be what the parent function of a constant looks like. Or here's a parent function of a linear. This would be x to the power of 1. Over here, this would be x to the power of 2, and this is x to the power of 3. So this polynomials, these are the different shapes you could see: a flat line, a diagonal line, a parabola, or a S-curve. Those are the shapes you could see based off the powers. Power 0, 1, 2, 3. Okay, so that's polynomials. We'll see polynomials today. In addition to polynomials, we're going to see a square root function. I don't know if I've shown you that graph in the first 11 lessons that we've covered so far. So you'll see a square root. What a square root is, it's half of a sideways parabola. I'll put the dots this way. You see if I put it down here, what does it now look like with this dotted line? A sideways parabola. Well, a square root is half of that. That's what it is. It's going to look like that. So you'll see a square root today. You will see reciprocal functions. This should say roots. Roots and radicals are the same thing. I should say roots, reciprocals, and absolute values. So reciprocal looks like 2 C-curves, like this. This is when you're dividing by a power of x. By the way, a root means that it's x to a fraction power. Square root is a power of 1/2. So if the first page had the power 0, 1, 2, 3, here we're seeing the power 1/2. A reciprocal is the same thing as a power of negatives. So this right here, we could rewrite that as x to the power of -1. So if you have a negative power, that's technically a division power of x. So this is if you have a fraction power, you get like a root. If you have a negative power, you get a reciprocal C curve. Okay. Now coming down, we now have absolute value. Absolute value, look just at the right side. If you only looked at the right side, what does it look like? Straight line. Diagonal line, but a line. What does the left side look like? Straight line. Okay, it is linear except for one thing. How is this different from a line? What's the linear parent function? What's the only difference? Yeah, because it bends because with absolute value, you have no negatives. This is how you, in the real world, model distance. So put that on there. It's linear, but without any negative portions. This is for distance. That's mathematically the only way to properly to show distance is distance have to be positive. Consider this. When you come to school, whether you walk or you drive a car, let's use driving a car. And someone drives a car, you know, they have a little odometer there that counts the miles. When you drive to school, let's just pretend that it takes 2 miles to get to school. When you drive home and you go the opposite direction, does your odometer show you that it took -2 miles to get home? So when you go the other direction, it doesn't turn it and go negative? No. What if you put your car in reverse? Does it then say negative? No, because it's counting distance, and distance is always positive. Mathematically, that's how we handle it. So you'll see absolute values. It'll look like a V. Notice there's no negative values, no negative y values. Okay? And finally, the last parent function we might see is what we call the greatest integer. This is real world for rounding. Is use real world when you need to round. So let me give you an example here. You're with your buddy. You go to the gas station for a snack during lunch on a Saturday, not during a school day, because you're not allowed to do that. But on a Saturday, you go to this gas station for lunch, and they ring it up, and they say it's $4.02, and you realize, oh, left my wallet at the house. Do you look at your buddy and say, hey, can I borrow $4.02? No, what do you actually say?
Can I borrow $5?
Can I borrow? You might say $5 at first. If you're my wife, this is the way my wife always works with me. She first says, can I borrow $4? Sure, I give her $4. She's like, well, actually, I need a little bit more. But either way, she's rounding it. That's what she's doing. So we go to the store and something's $15.99. You know what she tells me? It costs 50. No, she didn't tell me it costs 20 because she knows I'll say no. What does she say instead? It's $15. She just rounds it down. It makes it sound more appropriate. Or we're running late. Here's another one. We're running late. I got 5 kids. It's the story of my life right now. Always running late. It's impossible to get 5 kids there. Okay, she looks on the map and it says it'll take 23 minutes to get somewhere. You know what she texts them? She doesn't say, we'll see you in 23 minutes. You know what she always says? We'll see you in like 20 minutes. Now, what's she doing there? She's rounding. That's what this is. Notice here, you only have whole numbers. So this value is 0 all the way up until this point. Remember, it's undefined at an open circle, and it jumps up to 1. It goes from 0 to 1. Did we have a 0.5 in the range in here? No, you never hit a half. You never hit, I'm talking about the range here. You never hit a half. You never hit 3/4. You just jump from 0 to 1, and then from 1 to 2, and 2 to 3, and so on. That's what greatest integer is. That's rounding. All right, with all that, we're now done. That's the parent functions you're going to see today. Let's talk about transformations. I told you you'd see 3. The first one we're going to see is a reflection. This is where you flip your values. What we're going to do on a reflection is we're going to negate. Write the word negate. You're going to hear me say that today. You're going to negate the values. Now, why I'm saying negate is because it would not be proper to say we're going to make negative. Here's why. If you have a negative number and you negate a negative, what is negating a negative actually going to make happen? It's going to go positive. But if you have a positive and you negate it, it's going to become negative. So when I say negate, I'm saying we're going to change the signs. That's what a reflection is. A huge note you need to write down. When you reflect, which direction is this reflecting? Let me draw you a point. Am I reflecting horizontally or vertically in this picture? No. When you reflect vertically, which axis do you actually cross over? Ah, see, y'all are saying things, guessing, and then you're looking and you're correcting yourselves. Let me say that again because we said both y and x. Let's make sure we say it right this time. When you vertically reflect, which axis do you actually cross? People are still getting it wrong. Look at the picture. When you reflect vertically, which axis am I crossing? The x. This is tricky for students. Here's why. When you reflect vertically, you are parallel to the y, but they will never ask you, what are you parallel to? They're going to ask you, which axis are you crossing over? A vertical reflection, though it's parallel to the y-axis, actually crosses the x-axis. Does that make sense? Okay, so let's make a note. It says it right here in the x-axis. Draw an arrow. Just make sure you see this back and forth. A vertical reflection crosses the x-axis. Okay, and now let's make the same note over here. This time, what type of reflection do I have? A horizontal reflection. So go ahead and put, this is a horizontal reflection. And if it's a horizontal reflection, though the reflected pieces are parallel to the x-axis, that's not what they're going to ask. They're going to say, which axis did you cross? You're crossing the y-axis. If you're reflected in the y-axis, it's a horizontal reflection. Now we have two more transformations. We're going to reflect, dilate, and translate. Okay, on translations, the next slide. Translations, what this means mathematically is happening is you are either adding or subtracting. So there's either addition or subtraction. So a reflection, the mathematical process is you negate. For translations, you add or subtract. All right, now this picture has a little bit of an optical illusion on the left side. When you look at the left side, it appears the graph got stretched or shrunk. Does it not appear that way? It's an optical illusion though. Let me show you what I mean. If I highlight this one and, oh my goodness, it's so hard for me to do it on this little board here because I can't see what I'm writing on. If I try to color that perfectly, that's the width here. When I slide it down, how do the widths compare? They're the same. There's an optical illusion here that it looks like the widths are changing. They actually don't. A translation, you do not change the width. You only change, like the vertex in this case. You just shift the graph over. So that's what's happening on a translation is you shift the graph. Now these two is not an optical illusion. You can tell the width did not change. You just shifted to the right. Or in this case, we shifted to the left. All right. And finally, the last one on the next page. The slide here has a typo. Scratch out the word translation. We're not doing translation on this page. This page we're taking care of dilations. Okay. If you dilate something mathematically, what you're doing is you're either multiplying or dividing. Multiply, or to keep it the same as everything else, multiplication or division. That's what's happening this time. When you multiply or divide, now we're changing the width or vertically how tall or narrow it is. So, narrow and wide would be a horizontal dilation. Narrow and wide is a horizontal dilation. How tall or short, that would be a vertical dilation. This happens by multiplication or division. Those are our three transformations. So Let me think. If you've ever gone to the eye doctor and they wanted to check your eyes, they put some drops in your eyes and it changes your pupil. You know what I'm talking about? Yeah, what do they call that process?
Dilate.
Dilate. Why do they call it dilating your eyes?
Because they make them bigger.
Because they're making your eyes bigger. Are they shifting your pupil?
No.
Are they making it roll up in your head or anything like that? No. They're putting it in there and it's making your pupil get real big. That's why they call it dilate. Dilate means to either make to stretch or to shrink, to make bigger or make smaller. That's what's happening here. Okay, so that's what that word means. With all that, let's get started. What I'm going to do all through this lesson is I'm going to give you an equation and I'm going to show you 1, 2, 3 different representations of how mathematically what's happening. Okay, so let's begin on this first one. It says use the function f of x equals x cubed. Yeah. Use the function f of x equals x cubed to graph and describe the transformations that have occurred if g of x equals negative f of x minus 1 minus 4. Wow, that's a lot of math there. Here's what I want you to do. First thing, come over here, and I want to make sure mathematically you understand how to get the y values. Our f of x equation in this case is x cubed. To get our y values, how can we get y values without using our calculator? I'm going to try to use no calculator today as best I can until the very end. You just substitute that value in. So what I'm going to do today is I'm going to call out the math and you call back out the answer. So in this case, I'm going to say negative 2 cubed. And you'll tell me negative 2 cubed is negative 8. Okay, what is negative 1 cubed? Negative 1. 0 cubed? 1 cubed? 2 cubed? And 3 cubed. That's not 9. 3 times 3 is 9 times another 3. 27. There you go. It's 27. Okay. Now, what we're going to do is come over and look at our transformations. An important key for us to understand is that when we look at transformations, anything that's on the inside of an equation is going to have a horizontal effect, and horizontal are always liars. So here, I want you to highlight or draw attention to this x minus 1 and put a liar here. Because you've heard me say this before, I will say it again. Your x's are always liars. That's why we dump them. Your y's tell you the truth. That's why we marry them. So here's how I'm going to write this. I'm going to call this one over here. I'm going to add some to our notes. I'm going to call this x1 and this y1. What I'm going to do in the second column is I'm going to tell ourselves what the x2 values will be. The x2 values are going to be, you take your x1, and what am I going to do if the equation says minus 1? We're actually going to add 1, and here's why. You take your, this would be like the x2 right here. You would say x2 minus 1 is equal to x1. And then what's the math required to get that? You would add 1 to both sides. That's why it mathematically works that way. Normally when we do this, we find the 0. But in this particular case, we're not finding a 0, but I'm stating what the x2 value would be. So it's going to be x1 minus, or plus 1. So here's what I'm going to do. I'm going to give you the x and the math, and you tell me what value we should write down. What is a negative 2 plus 1? What is a negative 1 plus 1? What's a 0 plus 1? What's a 1 plus 1? What's a 2 plus 1? What's a 3 plus 1? That's how this x values would change. Now the y values. These are truth tellers, so this is easier. This is saying we need to negate the y's and then subtract 4. So I'm going to do negative y1 and then minus 4. Okay, so we're going to negate our y's and then subtract 4. So you ready? Negate negative 2. 2. Subtract 4.
Negative 2.
Negative 2 goes first. Negative 2. Good. Let's try it again. We're going to negate negative 1. 1. Subtract 4. Negative 3. All right. Negate 0. 0 minus 4. Negate 1. Negative 1. Subtract 4. Negate 8. Negative 8. Subtract 4. Okay, so I'm taking the y values now. I'm looking at these. So now negate, what value should I say next? Negate 27 minus 4. Negative 31. That would be my table. So that's one way you could get tested on it, is just making up a new table. So now what I'm going to do is I'm going to plot those points, and we're going to now look graphically how this would look. So negative 2, negative 8. You would go left 2, down 8, plot that point. And then negative 1, plot that point. All right, we got a correction here. So it's not negative 2. So negative 8, negative of negative 8 is positive 8. Subtract 4. We got 4. Did I mess up more?
Yes, because we the whole thing.
Are you sure? Negative of negative 1 is 1. Subtract 4. Negative 3. That was right. Negative of 0. Just the first one. Okay. Sorry that threw y'all off. Glad you stopped me. Okay. What about, we have 0, 0 here. Oh, going back to the graph. We've got 2 points graph, so let's go 3 points here. 0, 0. 1, 1. And 2, 8. Those are the only the points I could fit on this first graph. Okay, so this is an S curve because it's x cubed. Draw your S curve and make sure you label it with an F. That should have an F above it just so you keep track of the equations. There's the parent function for a cubic right there. That's the parent function for a cubic function. Now we're going to graph g of x, the transform graph. So let's plot these points. At negative 1, we're at 4. So negative 1, 4. 0, negative 3. 1, negative 4. 2, negative 5. 3, negative 12. I can't fit that one on there. That would be down here somewhere. I can't fit that one down there. So I'm going to connect those points, and we'll have our graph of g. That is g right there. So that's a second way, a second representation of how you could be tested, quizzed, or see this come up on homework is by graphing. That's how you transform a graphic from one to the other. All right, now let's talk about how it changes our domain and range. For domain and range, here's how the easiest way to explain this. There are 3 types of numbers in math. There's negative numbers, there's 0, and there are positive numbers. Those are the only 3 types. Let's say it again. What types of numbers are there? Negative, 0, negatives, 0, positives. Okay, for the parent function, you're going to have some combination of those 3. Many times, it's all reals. Let's check our rules. For domain of the parent function, for the parent function, those are the only values you're going to have. Zeros, negatives, positives. X cubed, there are 3 rules that can break up a domain. One is division. Does x cubed divide at all? No, so still all reals. Does x cubed have a square root? No, so still all reals. Does it have a logarithm? No. This domain should be all reals. You could put any x value in, it's going to be all reals. So I'm going to say from negative infinity to positive infinity, and I'm going to show you why later. You could do XER, but I'm going to show you why later today, why I'm doing this symbol as we go through. So I'll do OR here. Yeah, go ahead. So that's all reals. Now, I want you to look at the y value. So again, the parent function is either going to be all reals, negatives, positives, and 0, or it's going to be a combination of those values. Tell me about this blue graph here. Does it, range-wise, we're talking about y's, does it have negative y values? Does it have the 0 y value? Does it have positives? It's also all reals. And again, if you wanted to, you could say YER. Or write it like that. Now, over here, what you would do is you would add 1 to the domain, because that's what the transformation was. So what's negative infinity add 1? Still negative infinity. What's infinity add 1? Still infinity. So this would stay as negative infinity to positive infinity. I'm just going to write it this way. What about here? On the range, it says negate and then subtract 4. What's a negative of negative infinity? Positive infinity. Then you take away 4. It's still an infinity. But this negative infinity, when you negate it, becomes a positive infinity. So it actually goes on the right side. This will, when we do this, it's going to flips. They're going to flip the order. I'll show you. Okay, now we plug in the positive infinity. What's a negative of positive infinity? This becomes, stay with me here. When you plug in positive infinity, it's negating a positive infinity. It becomes a negative infinity. Then you subtract 4. It's a negative infinity. So what am I saying? When you have a negative, I want you to see this. The values will switch order. You see how the negative came first in positive? When you come over here, this one led to the negative. This one led to the positive. You need to switch the order to be mathematically correct. Now, on this one with infinities, it doesn't matter. It will matter later when we start getting numbers involved. Okay, so I just want to point that out, that when you have a reflection, it's going to flip these two values, the order around. It's hard to tell on this one. It's going to come though. All right, last thing before I move on. What do you call a negative? Is that a translation, a dilation, or a reflection?
Reflection.
That's a reflection. What's this?
Transformation.
Transformation means any of those three.
Oh,
It's a
translation.
translation, and this one?
Translation.
It's also a translation. That's right. Reflection, translation, translation. You know what? Maybe I should write that. Should we write that in? Let's write that in. This is a reflection. And these two are translations. Okay, let's try the next problem. So we're just going to kind of do this on repeat until you start getting it down. All right, let's look at part B here. This time it says use the function square root of x. So come down here. First thing we're going to do is I want you to write that f of x equals the square root of x. So I've given a host of different values here. When we would try to figure this out, you would first plug in -2. So I'm first just going to find the table for f here. -2. What's the square root of -2? Get that up, Christopher. Yeah, come on up. There is no square root, so we do undefined here. This is undefined. This is rule number 2. You cannot take a even root of a negative number. That is undefined. Okay. What's the square root of -1? It's also undefined. I'm just going to say UND this time. Okay. What's the square root of 0? 0. What's the square root of 1? Square root of 4. Square root of 9. And square root of 16. You got it. All right, now I'm going to jump over and we're going to do G. Now to call out the transformations we're going to have this time. What do you call something that's multiplying? That's a dilation. That's a dilation. What do you call something that adds? It's not a transformation. Transformation means any of those three. Translation. What do you call something that subtracts? These are both translations. Good. These are both translations. Okay. Now, for your x's, I want you to recall that this is kind of like the x2, if you will. So it's saying here, x2 plus 4 is equal to the original x1. This is why the x's are going to become liars. So how do I actually solve for this second x, this new x value? What math would I have to do to solve? We would subtract 4. And so what we're actually going to do to get our x values is we're going to say that x2 is equal to x1 minus 4. That's what I'm going to write in this column here. if I'm gonna call this one x1 and y1. How we get these values is we're gonna take x2 and say that it's equal to x1 minus 4. That's what I'm sneaking in here. So as I call them out, I'm gonna call out the math, you call out the answer back. It's a -2 minus 4 more. -2 minus 4 is -6. Good. -1 minus 4 more. -5. 0 minus 4. 1 minus 4.
-1. -3. -1.
1 minus 4 is -3. Okay, how about 4 minus 4? How about 9 minus 4? We shouldn't have negatives now. And what about 16 minus 4? 12. There we go. Now, the y's, I'm not going to do this math on the side because they're not liars. I only did this because it's a liar. So that's why I write that out, is that x's are liars. X's, that's just singular here. This x is a liar, and that's why I did the math over there. But y is a truth teller. So y should be quite a bit simpler. You just write down the math you see. What is that 3 doing to the f? It's multiplying, or if you said dilate, that's fine. It's multiplying, and then we subtract 2, which would be a translation. So that's what we're going to do for the y. So we're going to multiply by 3, then subtract 2. What is 3 times undefined? Undefined. Then you subtract 2. It's still undefined. Okay, how about the next one? What's 3 times undefined? Undefined, subtract 2. Undefined. What is 3 times 0? Minus 2. Okay, what's 3 times 1? 3 minus 2? 1. What about 3 times 2? 6 minus 2? 3 times 3? 9 minus 2? And finally, 3 times 4? 12 minus 2? Those should be the values here. So I start graphing 4 to the left, 2 down. Oh, I didn't plot these yet. Sorry, let me get these on. Parent function, we have 0, 0, 1, 1, 2, 3, 4, 4, 2, and 9, 3. 9, 3 would just be 1 block over. I can get that one on there. Make sure you properly label. I missed. Let me try again. So label that with an F there. Now we're going to plot these points. Again, you don't have to worry about the undefined points. So -4, -2, got that one. -3, -1. No, -3, +1. I'm sorry. -3, +1. I was about to make another mistake. How about 0, 4? 5, 7? 1, 2, 3, 4, 5, 7, and 12, 10. I can't get that one on there. There we go. So I've given you 2 different representations of the same problem. Just so you know, you won't ever have to do that all at once on one problem. That's 2 different representations. I showed you how to change it using tables, and then I showed you graphically how it's been transformed. Now let's go down and talk about how it changes the transforms, how the transformations, what effect they have on the domain range. I always start with the parent functions because it's the easiest. When you look at the domain here, we're talking about x's. Am I all reals? That means negatives, positives, and zeros? No. What do I not have? Negatives. I don't have negatives. Do I have 0? Do I have positives? So it's going to be from 0 to positive infinity. You don't have the negatives, and that's because rule number 2, you can't take the square root of a negative. Now let's look at range. Again, parent functions are the easiest, so go off of that. Because you just ask yourself, do I have negatives? For range, you're looking up and down. Do I have negatives? Do I have positives? Do I have 0? What do I have here? Positives and 0. You always start with the smallest number. So from 0 to positive infinity. Now I just apply the math. This says take my x values and subtract 4. Well, what is 0 minus 4? Negative 4. So my domain is negative 4 until, what's infinity minus 4? Still infinity. Your brackets and parentheses should not change. Now let's go to the range. This says take your multiply by 3, then subtract 2. What is 3 times 0? 0 subtract 2? Negative 2. Okay, great. What about 3 times infinity? Infinity minus 2? Still infinity. That should be my range. Okay? You've seen me do it twice now. Cool? All right, let's get a different parent function. What about this time? What symbol is that for? It's absolute value. Do you remember what an absolute value does to the equation? Changes any negative number and makes it positive. Azariah, can you sit up for me, please? Azariah, are you tracking with me? Can I see your pattern? Are you writing it down? Okay. All right. Let's write out the values then. So if I'm taking the absolute value, and again, this is dealing with f here. What is the absolute value of negative 2? 2. What's the absolute value of negative 1? 1. What's the absolute value of 0? Absolute value 1 and absolute value of 2. You just don't ever consider a negative if it's absolute value. Now I'm going to come over here and I'm going to label what transformations are taking place. I'll figure out the math on this. This 2 is dividing. What does that make it? That is a dilation. Good. Dilation is when you multiply or divide. What about this minus 3 or the plus 1?
That's translation.
These are translations. Good. These are translations. Okay, to figure out the lie, what I'm going to do is this is going to become x2. So it's x2, whoops, got dyslexic, x2 minus 3 over 2 equals x1. We got to figure out the lie. You would multiply by 2. So I'm going to have x2 minus 3 equals 2 times x1. Okay, then what else would you do? Add 3. And that's because the x's are liars. It's 2 times x1 plus 3. That's because these are liars. I'll put plural this time because there was 2 transformations. So that's what's going to go in this column. G is going to be made up of, for our x's, the x2 is going to equal 2 times x1 plus 3. So here again, I'm going to call out the values, and you call back the answer. I'm going to call out the math, you call out the answer. What is 2 times negative 2? Come on, everybody try here. 2 times negative 2 is negative 4. Add 3. Negative 1. Good. How about 2 times negative 1? Negative 2. Add 3. 1. How about 2 times 0? 0. Add 3. How about 2 times 1? 2. Add 3. And finally, 2 times 2? Add 3. Good. Now let's talk about the y's. What do you see happening on the outside of the equation? An addition of 1. That's the only thing that's happening to y's. So the y's, they're truth tellers, they're the easy ones. So all I'm doing to my y values is I'm adding 1. Okay, so I look at my y column, I have a 2. So what's 2 add 1? What's 1 add 1? 0 add 1. 1 add 1. 2 add 1. All right, let's plot that. That's our table. We've done our transformation there. That's one way of representing this problem. Now let's represent it a second way. Let's graph it. So in -2, 2, we have a point. -1, 1, we have a point. 0, 0, we have a point. 1, 1, we have a point. And 2, 2, we have a point. Those are our points. I'm going to connect those. These absolute value, if you remember, they look like lines. But the lines aren't negative. So there's the parent function for yourself. Now I'll plot these points. So -1, whoops, -1, 3. 1, 2. 3, 1. 5, 2. 2, 3, 4, 5, 5, 2. And finally 7, 3. This would be the graph of G. Notice because the word dilation is used, it should look either wider or skinnier. In this case, it looks wider. It says divide by 2. We didn't actually divide by 2 horizontally. We multiplied by 2. That's what made it wider. And we shifted off the origin. It was at the origin. We shifted right 3 and up 1 because the inside's a liar. It became a positive 3 on the x value. And then we went up 1 because the y is a true teller. So that's our graph of G. So there's 2 different ways you can see it. Now let's talk about domain and range. So looking at the graph, remember there's 3 types of numbers. What are the 3 types of numbers? Positives, negatives, and 0. Okay, when you look at the blue, does the blue include negative numbers?
No.
We're talking about domain right now, so you're looking at on the x values. Do you have negative x values? Do you have positive x values? Do you have a 0? Yeah, we do. So we have all reals. So you could write all reals, but for the sake of today, I'm going to put infinities because that's easier. Plugging in the math. Now tell me about the range. Is the range all reals? Do I have negative y's, positive y's, and a 0 y? I have a positive y and I have a 0, but I do not have negative. So we would go with a bracket from 0 until infinity like that. Now I'm going to do this exact same math over here on the domain and range. So what is -2, excuse me, not -2, what is 2 times negative infinity? Negative infinity. Then you would add 3. Still negative infinity. What is 2 times infinity? Infinity plus 3? Okay, so here's the rule. The only way an infinity can change is when you negate it. It can change from a negative to a positive infinity, but other than that, it doesn't change because you'll never be multiplying by 0 or anything like that. So adding, subtracting, multiplying by a number, whatever, will not change an infinity. The only way an infinity will ever change is the order from a negative to a positive if you negate it. That's the only way. All right, let's go to the range. This says to add 1. So what is 0 plus 1? 1. What's infinity add 1? Infinity. This will be a positive infinity. Okay? You might be having this down pretty good. But I'm going to make sure we all understand it. I'm going to pound it in one more time. I'm going to do it one more time, even though many of you could probably, at this stage, practice it. Go ahead. All right, so I'm going to show it to you one more time. What parent function do I give you on D? I'm giving you x squared. So we're going to take each x value and square it. What's negative 2 squared? Not negative 4. Negative 2 times negative 2 becomes a positive 4. Okay, what's negative 1 squared? 0 squared. 1 squared. 2 squared. 3 squared. There you go. Now our transform graph. I want you to think, look at the inside first. So inside's the horizontal transformations. I have 3/2 x, and I'm going to call it an x2 equals x1. Considering this is x1 and this is y1. How do I get rid of a 3/2? This is saying multiply by 3, divide by 2. What's the opposite? Multiply by 2 and divide by 3. If you did this, just check it out. If you multiply by 2/3 on each side, what's 2 times 3? 6. What's 3 times 2? 6 divided by 6 is 1. You're left with x2 equals 2/3 x1. That's going to be your formula here. For a fraction, if it's a liar, you just take the reciprocal. That's what you do. So it'll be 2/3 x1. You know, I did not ask. Let's mark out the transformations. What's a negative? That's going to be a reflection. And if it's on the outside, it's a vertical reflection, meaning it's crossing which axis? X-axis, good. Okay, multiplying by 2. What will multiplying by 2 do to it? It's dilation. And I'm going to make it plural because this also is multiplying. So these are dilations. This is a vertical dilation. This is a horizontal dilation. Again, x's are liars. So I'm going to put that over there. That's the lie. That's figuring out the lie. Okay, now let's talk about the y's. What does this say to do to the y's when you look on the outside of the equation? Negate it, and so basically we're multiplying by negative 2. So the y2 is going to equal the negative 2 times y1. All right, 2/3 is not going to be fun. What's negative 2 times 2/3? Or I should say 2/3 times negative 2. Negative 4 divided by 3. You've got it. You multiply the top, divide the bottom. Okay, what about negative 1 times 2/3? Negative 2 divided by 3. Okay, what about 0, 2/3 times 0? How about 1 times 2/3? What about 2 times 2/3? And last one, what about 2/3 times 3? 6/3, and 6/3 is 2. Very good. All right, now let's do the y2 column. So it's negative 2 times y1. What's negative 2 times 4? Negative 8. What's negative 2 times 1? What's negative 2 times 0? Negative 2 times 1. Negative 2 times 4. And finally, negative 2 times 9. All right, that's completed the table. We've now done that. Let's plot up our points and see what we got here. So negative 2, 4. Negative 2, 4 goes there. Negative 1, 1. 0, 0. 1, 1. 2, 4. 3, 9. This would be just off the graph. Be right there. Connect your dots. It would look like that. All right, and so I'm going to put an F there, label it properly. All right, there's my parent function. Now, when I graph up the transform functions, negative 4/3, that's like negative 1.3. Go to negative 1.3, I need to go down 8. That's all the way down here. Negative 2/3, that's like negative 0.6. And then 2 down, 0, 0, 1, 2/3, comma, -2, and then 4/3, -8. That's right down here. Connect those and you'll have your graph of G. All right, talk to me about domain. Domain, look on the parent function, f. Do we have negatives?
Yes.
Do we have positives?
Yes.
Do we have 0? All right, all reals. All right, so, whoops. Yep.
Are we recording any of the videos at your house?
No. It's chaos there. I got 5 kids. All right, so it'd be negative infinity to positive infinity. All right, tell me about the range. Looking at the blue here. You're looking at the blue. Do I have negative y's?
No.
Do I have positive y's? Do I have 0y? Yes, so it's from 0 into positive infinity. Okay, so now for the transformed, you need to multiply by 2/3. When you take negative infinity and you multiply it by 2/3, what do you get? Negative infinity. When you take positive infinity and multiply that by 2/3, what do you get? Positive infinity. It's still all reals. As you can see here, it goes. We have negatives, we have positives, we have 0x. Okay, now for the range, you take -2 and you multiply it times 0. So -2 times 0 is still 0, but that flip is actually going to make it become this value here. How do I know that? Because I'm going to take a -2 and multiply it times infinity. What's -2 times infinity? Negative infinity. That's the only way an infinity will change. And so I just want to draw the attention to that one more time. This is the second time you've seen that. If you have a reflection, it'll change the order of your values. So a reflection did that. We reflected the y values, so it switches the order of your domain and range.
Yeah.
All right, with all that, we have one for you to practice. Okay, picking back up. So now what I'm going to do here is I have one thing I needed to add to this. I didn't realize it. It's going to be hard. This time, what's going to happen is we're going to look at this graph, and we're going to, this time, start with the graph and get our values. I need to add 1 point to this because you can't tell exactly what happens just going off this 1 point to this 1 point. I want you to come over here, add a point right there on your graph. That value there. Add a point right here on the graph. And draw an arrow connecting the two so you can see how it's actually being transformed. But this graph is going from here to there. Go ahead and add that to your graph. So what I'm going to do is take the 2 points that are on the original. What's the parent function? What kind of equation makes this type of graph? It's an absolute value. Put absolute value right here. It is an absolute value. Now we're going to write down the location of these 2 points. So on the parent function, what's the location of that point right here? I hear 4, 4. It's actually -4, 4. And what about this point over here? This one is actually, this one's +4, 4. Okay, let's add that to the graph, that to our table. We had the point 4, 4. Now over here, let's talk about the transformed graph. This time, I'm just going to do x and y equals g of x. Okay, tell me about the location of this point right there. -1, comma, -4, good. That's -1, comma, -4. And what about this point there? +1, -4. +1 and -4. You know what? Just to stay consistent, maybe I should stay with the x2. Okay, so tell me, how do I get from my x1s to my x2? What did I do to get from -4 to -1 and +4 to 1? I hear subtract 3. But it's actually, if you took away -4 and you subtract 3, you get -7. So that's not it. So, well, okay, what if it's plus 3? Well, -1, a -4 plus 3 is -1, but 4 plus 3 is 7. So it's neither.
Divide by four.
Divide by, yeah. You divide by what number?
4.
It's x1. Oh no, it's freezing up on me. Should be x1 divided by 4. You got it. We take our first x and we divide by 4. All right. Now let's talk about the y's. A positive 4 became a -4. A positive 4 became a -4. We negated. Okay, so there's how the table should look, and we figured out the pattern here. Let's talk about the domain and range. Looking at the parent function, I always start with the parent function. For domain, that means x value. Do we have negative x's? Do we have positive x's? Do we have 0? So it's all reals. This one, I've been doing blue all day. I have it in black there, so I'll do it in black. It goes from, goodness, my board's slowing down on me. From -infinity to positive infinity. Okay, tell me about my range. Do I have negative y's? No. Do I have positive y's? Do I have 0? So it's from 0 until positive infinity. Good. Now, for my transform graphs, will I have negatives? Oh, wait. Let me just do the math. You take your x1, negative infinity, divide by 4. What's negative infinity divided by 4? Negative infinity. You take your positive infinity, you divide that by 4. Still positive infinity. Okay, now come over here. We take the 0 and we negate it. What do we get?
We get
0. So should I do it like that?
No,
Why not?
It's a reflection.
So reflection, it's now going to switch sides and it's going to become the larger number. Okay, now I take positive infinity and I negate it. It's going to become a negative infinity. Very good. And again, that's because of a reflection. Now, how would the equation look? Negative goes on the outside. So it'd be a negative f. And then the inside, we don't actually divide by 4. What's the opposite of dividing by 4? You multiply by 4 like that. That would be your equation. If you want to make a note that these switch, you can. And that switch because of why? The reflection. Now, anytime you have a reflection, your domain, largest and smaller number will flip. All right. One more time. All right, we'll call this x1, this y1. Looking at this graph, do you remember what type of function makes C curves? Reciprocal, very good. That's 1 over x. Let's write out these two values. What's the coordinate point right there?
Negative.
-1, -1. We have -1, -1, and then what about this point right there? Positive 1, 1. Is that point? Okay, so we have positive 1, 1. Okay, now let's look at the coordinates of these 2 points. So talk to me about this point. This one moved over here. -3, -1. So we have -3, -1. And then what about this point? 3, 1. All right, how do we get from -1 to -3 and also from 1 to 3? What happened? We multiplied by 3. Now, what do I do for my y's? I don't do anything. All right, let's talk about domain. This one's a little trickier. Start looking at the black graph. Do I have graph on the left side? On the negative side? Yes. Do I have graph on the right side, the positive side? Does the graph hit 0? No. So you cannot be 0. So remember how we said we can write this? We can say x cannot be 0, but what can it be?
Everything.
Everything else. You could do it this way. I'm going to do it that way for simplicity's sake. All right, and now tell me about the range. Do I have negative range? Do I have positive range? Do I have zero range? No, so this is very similar. It cannot be zero, but it can be everything else. Okay, now I come over here to my domain and I'm saying, hey, you know what I need to do? I need to multiply this all by 3. So what is 0 times 3? And I didn't color coordinate this here. So I'm going to do so now. There you go. So when I multiply that by 3, I get that x cannot be 0. 0 times 3 is still 0, and then all reals times, all reals times 3 is still all reals. Okay, and now for the y's, it's just equal. So nothing changes whatsoever. You could take your pencil, right click, and just do copy and paste on your paper. Bad joke. Okay, that joke. Won't tell that one again. Got it. All right, let's talk about the equation though. This says to multiply by x by 3 and do nothing to the y's. Do I actually multiply by 3? No, what we do is we need to divide the x by 3. This is a little tricky on a reciprocal, so I'll show you how it works one time, and it'll probably hopefully it'll make sense. What you do is it's 1 divided by x, but the x needs to be divided by 3. Now, do we leave a fraction divided by a fraction? What you learn in earlier years is what you can do if you have a fraction divided by a fraction, or in this case, an integer divided by a fraction, is you can take your value and you multiply by the reciprocal of the second fraction. So I take that reciprocal like that. Now, when I multiply that out, what is 1 times 3? And then the 1 times x is still x. Now, this is why this should make sense, is you're dividing the x, but in this case, in the problem, x is actually doing the dividing. So instead of putting 3 with it, because that would be multiplying, you put it on the opposite side. That's the shortcut. So the 3 just goes to the numerator. That's your equation there. Questions? All right, I have done a million of these. You ready for your turn? All right, I'll let you take this point to this point, see if you can figure out what happens. DOL number 2. I'm going to add 1 point just to make sure no one has a math error. A very easy point to work with. I would add this point in here and this point there and have an arrow going from this one to that one as well. That way you don't have a simple math error, because just with 1 point you can't tell exactly what's happening. So make sure you have both of those points. I would add that in like that for your DOL number 2. Okay, as we pick back up, I'm going to do a summary real quick. The 2 things that are really, really important for you to understand. Number 1, horizontal transformations occur on the inside of the equation. Anything that's on the inside, meaning it's going to affect the x's. Let me go back to a problem here. Anything that happens on the inside affects which values? X's, and they are liars. Anything that happens on the outside changes the y's, and those are truth tellers. If I were to summarize the whole lesson, that's it. Inside lies. Inside is your x's, and they lie. Outside is your truth, and that's your y's. X's lie, y's tell the truth. All right, let's finish this up. Example 3a. It says the function a has this domain and this range. The function g is given by this. What are the domain and range of g? So what I'm going to do here is I'm going to take away all the graphing, all that, and just get simple math. So I want you to see it just following the simple summary I gave you. The domain of f, I'm going to write it this way. The domain of f is -3, 4. Whoops, with a parenthesis. Now, if I wanted to find the domain of g, how would I change the domain of f? What do I look at if I'm doing domain? Do I look at the outside or the inside? Inside. Okay, so remember, this is like saying 2 minus x2 equals the x1. Because these are liars. This is how you take away the lie. So what would you do first if you were solving this? I hear subtract 2. 100% agree. We would first subtract 2. So negative x2 would equal x1 minus 2. And then what would you do? This is like multiplying by negative 1. What's the opposite of multiplying by negative 1? Then you would divide it by negative 1. So x2 will be equal to, basically you could write this as a negative x1. And then what's a negative of a negative 2? Plus 2. That's when you take away the liars. Okay, so again, those are the liars. So here's how this would look over here. Remember how we first subtracted 2? We need to first subtract 2. This is my first step. When I subtract 2, what do I get? When I subtract 2 on each side, I get negative 5 and 2. And then what did I do second? Then we divide these by negative 1. Now that's a reflection. So what happens to my order when I do that? They switch. So this 2, positive 2, that's second, now becomes a negative 2. And this negative 5 becomes a positive 5. It's the second value. This right here is the domain of G. That becomes the domain of G. Now let's reload and try this again. The range of F is negative 4, negative 1. Now this is going to be easier because this is truth tellers. What does it say to do on the outside of this equation? Multiply by 4 and subtract 1. So we have a dilation and a translation. So PEMDAS, you need to multiply first. When I multiply, what do I get? Negative 16 and negative 4. And then we subtract 1 to that. And so when I subtract 1, I'm going to have the range of G. What is negative 16 minus 1 more? Negative 17. What's negative 4 minus 1 more? Negative 5. Y'all right. Negative 5. Now, why did I not change the order this time like I did up earlier? That's right. There was no reflection of the y's. It was only a reflection of the x's. You know, I didn't put that here, that these switch the orders. Those, when you reflect, they switch the order like that. That just looks too messy, so I'm going to leave it that way. All right. Here we go. Part B. Function f has domain and range here. Domain and range. So I'm going to say domain of f is negative infinity to positive infinity. I'll do the range in a moment. G is given here. How do I change the domain? How does this say to change the domain? You're looking on the inside. It says to multiply. It's a liar, though. So what do we do instead? We're going to divide by 2, both values. Both values get divided by 2. And just like that, we'll have the domain of G. What is negative infinity divided by 2? Negative infinity. What's infinity divided by 2? Still infinity. There's my domain of G. There's the domain of G. Okay, now let's talk about the range. The range was given to us as negative 2 into positive infinity. When you look at these values, what effect do we have on the range? We multiply by negative 3 and, okay, according to PEMDAS, which one goes first? We multiply. Whenever you multiply by a negative, what's going to happen?
Yeah, positive.
It's going to positive, and this is going to become a negative. So I need to switch my order. So what's negative 3 times infinity? It's a negative infinity. What's a negative 3 times a negative 2? Positive 6. Now we add 5 to that. And we're going to have our range. What's negative infinity plus 5? Negative infinity. What's 6 plus 5? 11. There it is. That would be the range of G. All right, you have a DOL to try. And after that, all I have here is I have a visual. If you want to scan this QR code, you can see this play out, how everything's transformed. I created a visual aid for you. This is not Max for Max work. This is to show you visually how it happens. You can play on this on your own. Don't forget about your AP Classroom as well, seeing those questions. But here's your last DOL here.